Okay, so this video is all about modern physics, just dealing with the energy. We'll get to the subatomic particles and quarks and things like that in the last video. So one of the first things you need to know is that a photon is essentially a particle of light, and that light has something called duality, in which sometimes it acts as a wave, such as there's wave interference and diffraction, other things, and sometimes it acts like a particle. And one of the ways in which it acts like a particle, and sometimes I'll ask this specifically, is because of the photoelectric effect. And we'll talk about the photoelectric effect in a few minutes. Now, when we talk about the energy of a photon, okay, that's equal to Planck's constant times the frequency. Okay, so if we know the frequency of light, we can find out how much energy that specific photon of light has. If we know how much energy the photon has, we can find its frequency using this simple equation. And this is a direct relationship between the energy and the frequency. As the frequency goes up, the energy goes up as well. Now, another way we can write that equation is that the energy of the photon equals Planck's constant times the speed of light over the wavelength. Okay, that's simply taking frequency and saying that it's equal to the speed of light over wavelength from this equation here. And when looking at these two things, you'll see that the energy and the wavelength have an inverse relationship. So as the wavelength increases, the energy of that photon decreases and vice versa. Now the photoelectric effect, this is an important one. Now the photoelectric effect deals with the photon imparting its energy to the electrons in a metal. So let's say you have some sort of metal here, and you have a light source, okay, and that light source is sending some sort of light down onto that metal surface. Okay. Now, if the frequency, which remember is related to the energy, is high enough, it'll actually knock electrons off of that metal and can send them elsewhere. So we call it the photoelectric effect. Now, the higher the frequency, the faster the electrons will move, faster they'll leave. We'll talk more about that when we talk about energy levels and electrons jumping energy levels. So if we want the electrons that are being knocked off here to go faster, then they're going to have higher frequency light. Now, if we make the light brighter, so there's more light coming in, increase the intensity. If the intensity goes up, that's an S, by the way, then there's just more electrons. Oh my goodness, more electrons. All right. So the frequency makes them travel faster, the intensity makes them emit more. And different metals react to different frequencies. Sometimes a frequency, there may be a minimum frequency required to create a photoelectron off of a metal. So anything below that minimum frequency is not going to cause a photoelectron to be ejected. Anything above would cause that to be ejected. Now, if we look at the energy levels, there's two graphs in your reference tables that deal with the energy levels, one for hydrogen, one for mercury. And they have their ground state, and then there's levels all the way up, and they get pretty tight at the top until you get to the ionization. Okay? So when a photon gets absorbed, the electron here will jump levels. Okay, it moves up levels. And the energy of that photon is equal to, that's a P by the way, is equal to the initial energy and energy from the energy level minus the final energy from that energy level. If a photon is emitted, okay, so it kicks out a photon, that means that that electron is jumping back down. So this is absorbed, and this is emitted. Okay. Same scenario. We can find out the energy of that photon that's emitted by finding the change in energy levels of that electron. Now, the energy of that photon has to match the change in energy of the electron exactly. So in order for an electron to jump up to, let's say, this level right here, it has to absorb exactly that amount of energy. The only exception is if it ionizes the electron. So let's say for hydrogen this is 13.6 electron volts. So let's say it absorbs 15 electron volts. So that takes it well beyond the ionization point. So 13.6 electron volts go to ionization. The other, whatever's left over, which would be 1.4 electron volts, goes to the kinetic energy of the electron once it leaves the hydrogen atom. Okay. Now, that change in energy of the electron, we can use that if we convert the electron volts to joules using the cover of your reference tables that tells you how many joules are in an electron volt. And then we can use that in the equation E equals HF, and we can find out the frequency of the photon that was emitted, and therefore find out what kind of light it emitted. Maybe it's a color, maybe it's ultraviolet, whatever it may be. Now, if we go back to the energy levels, let's say we start out at n equals 1, and this is n equals 2, and this is n equals 3, and let's do another one, n equals 4. Okay? And it says that a photon or electron drops from n equals 4 to n equals 1. And it wants to know how many different kinds of photons could be emitted while that electron drops from 4 to 1. Okay? We have to look at all the possibilities of jumps that it can make. So the first one could be 4 to 1. Okay? Another one could be 4 to 3. It could do 4 to 2. It could do 3 to 2. It could do 3 to 1. It could do 2 to 1. Okay? For a total of 6 different frequencies that could be emitted. Okay? You have to look at all the possible jumps for that electron as it goes back down. And just remember, one major thing. If we're using this equation here, okay, or this equation here, or this one, which is just a rewrite of the first one, our energy must be in joules. You cannot use electron volts for your energy on that. They may give you information on electron volts, but then you have to convert it into joules in order to do that calculation. And the next part we'll talk about all the subatomic parts of modern physics, and we'll get into quarks and baryons and mesons and all those fun things.